Elijah, for giving me a chance to present my recent work. So today I'm going to talk about some how we can construct dual geometry of the some quantum field theory data. So in this case, I use some deep learning technique. So this is why I use the deep learning technique, because it is so there's some technical some problem to find some dual geometry. I will explain later. So so due to that technical reason, we use the deep learning technique. So this is simply minimize the error from the data. So this work is based on our some recent papers, which was collaborate with some Professor Chanyong Park and Dr. Sejin Kim and student Chanyong. So Sejin Kim and Chanyong are expert in some controlling some machinery better than they are better than me. So unfortunately, I'm not an expert in machine learning. So in this talk, I skip the many details of the deep learning. I will focus on what is some motivation of this work and what is the result of this work. Okay, so this is the motivation. So because I'm working the research area related to some ADX correspondence. So the one of the main goal of this ADX correspondence is to understand the non-perturbative picture of the quantum field theory. So but unfortunately, so ADX correspondence is well defined only some specific geometry and specific field theory, because so to consider the to explain some correspondence between the geometry and component field theory. So usually we need very large symmetry like component field theory and supersymmetry. But if you impose such kind of large symmetry, then the theory becomes trivial, because usually there is a non-trivial algebra, and the theory is scale independent. So, however, in real physical system like condensed matter and QCD, so usually those kind of large symmetries do not exist. So we need to break such kind of the large symmetry. But ADX correspondence is well defined in some supersymmetric theory, like N=4 superharmonic theory. So, okay, so from some component field theory point of view, so it is very interesting to understand the IR physics. But we are working in the high-energy physics. Usually we know that some fundamental theory, which is so well defined in the UV region. So to understand the IR physics from some microscopic theory or fundamental theory, we need to understand the algebra. But usually, so IR physics is appear in strong coupling limit. So we need to know the non-trivial, non-perturbative. We need to know the non-perturbative algebra to understand IR physics. So that is one big problem in quantum field theory. So it is not easy to solve that such kind of the non-perturbative algebra equation. In string theory, we know that if we following this ADX correspondence, then the ADX correspondence claim that the gravity theory matched or some map to some non-perturbative algebra flow. But unfortunately, so usually if you consider some simple geometry, then so we don't know what is some dual quantum field theory. So that makes some problem. So if we want to understand some algebra of the real physics, So in that case, we don't know what is the dual geometry. However, if we can find some dual geometry of the real condensed matter system, then we can apply the ADS-shaped correspondence to understand the IR physics. So it is important to know that some dual geometry of some condensed matter system. So here, so this is sorry. Oh, okay. So this is some usual path to understand IR physics in quantum field theory. However, if we apply some ADS-shaped correspondence or some duality, then you can going around this non-trivial trajectory. So if we using reconstruct the dual geometry of the such kind of the quantum field theory, then we can understand IR physics by simple classical gravity theory. So that is the big motivation why we study the duality of the gravity and quantum field theory. Yeah, so here, so I consider some simple example. So people considering the condensed matter physics. So in this case, I focus on some thermodynamics. So thermodynamics can be understood as some IR physics of the quantum entanglement to entropy. So usually the entanglement to entropy follow some thermodynamics like law. It's very similar to the thermodynamics law, but so this is simply it's almost same, exactly the same as the thermodynamic relation. But so in this case, the temperature is not the thermal temperature. It's some kind of some new concept comparing the ratio of increased ratio of the energy and entanglement entropy. However, so this is not the same as the thermodynamics law, but if you consider, it was known that if we consider some algebra of this entanglement entropy, then in the IR limit, this entanglement entropy thermodynamics law reduced the well-known thermodynamic relation. So in this picture, so we can understand the thermodynamics.
E on the right hand side.
Oh, this one?
Yeah.
Oh, so this is called entanglement temperature.
No, E. What is
Oh, this E. Yeah, this is the internal energy of the system. Yeah. So energy is this is a thermal internal. So E is the same, but the difference is this energy is the total internal energy of the system, but in the here, so this energy is only the internal energy included, some subsystem.
Okay, I have a question. So,
Yeah.
For the UV case, can you say the thermal equilibrium?
No, so so usually thermal concept that is a microscopic property. So we need some many particle system. But if we focus on the UV theory, so in that case we consider only some dynamics of the particle. So in the UV theory or fundamental theory, some region there is no concept of the temperature. So the temperature entropy is some emergent concept in the macroscopic system. Okay.
How we can define that relation?
Oh, this one.
Yes.
Oh, yeah. So it is. Let's see. Yes. Oh, let's see. Unfortunately, I didn't skip the detail of this theory. So this is what if you consider some to define the entanglement entropy, we first need to define the modular Hamiltonian. Then we can define the modular Hamiltonian. Then the left-hand side is related to modular Hamiltonian. So that change is directly related to entanglement entropy change. So that is called thermodynamics like law. So in this case, so probably E divided by TE is a change of the modular Hamiltonian. Yeah, so this is some specific case. It's not the general case because so this theory allowed some IR, some summarization, but in real condensed matter system was some QCD, so we cannot claim that. So always, so such kind of the thermodynamic limit is exists. So here, just we focus on the some specific case, which some theory allowing the such kind of the some thermodynamic limit. So usually entanglement entropy is determined by this one. So usually the entanglement entropy is proportional to the so depend on the some subsystem size. Only there is some data. So starting from this data, we want to reconstruct the dual geometry. So that is the main goal of this theory. Okay, so one important thing is when you consider this thermodynamic case, so entanglement entropy usually shows that the area law, because in the macroscopic case, so we can consider two kinds of the correlation. One is the short distance correlation and long distance correlation. In the microscopic theory, so short distance correlation is important. So short distance correlation is appeared near the some entangling surface, which is the some boundary dividing two systems, subsystem, and it's in complement. So usually that short distance correlation is proportional to the area law. So this is the reason why we obtain the area law in entanglement entropy. However, if we consider IR limit, then the long range correlation becomes more dominant than the some short distance correlation. So if we consider long distance correlation in the IR limit, then usually volume law is appear. So here, so entanglement entropy is not extensive quantity in UV theory, but in the IR region, so the thermal entropy, which is the some main contribution to the entanglement entropy in the IR region, so which is proportional to the volume. So in this case, thermal entropy is usually appears as an so external quantity. Extensive quantity. Okay, so so here we focus on the some theory which allows some thermodynamic limit in the IR theory. Then we want to reconstruct the dual geometry. So the existence of the thermodynamic limit indicate that the dual geometry should be black hole type, right? So we expect that, okay, the dual geometry of such kind of theories is a black hole. So we consider some general black hole metric. So, but in this case, F is not determined yet. So that should be determined by from the some quantum field theory or entanglement entropy data. So the typical picture of the black hole is the black hole should have the horizon, right? So this indicates the horizon, and there is some another function which is should be regular in the entire, the outside of the horizon. So this is a typical form of the black hole geometry. So here, unknown factor is a horizon and this regular function. If we define this horizon and regular function, then we can exactly determine what is the some dual geometry. So how we can determine this one? So as I mentioned before, we use the entanglement entropy, which is a quantity of the quantum field theory. So in this case, the entanglement entropy only depend on the subsystem size. So here, so there's no any information about so horizon and regular function. So anyway, so if you extract some information of this horizon and regular function from that entanglement entropy, then using this one, we can understand some other or all thermodynamic property of the system in the IR region, because so using the some Hawking's and Bekenstein's law and also thermodynamics law, we can determine the temperature and entropy and internal energy from this result. Okay, so all these quantities depend on the horizon and the regular function, the value of the regular function at the horizon. If we know determine these two things, we can exactly understand the all IR thermodynamic property from the entanglement entropy. Okay, how we can make this construction from the entanglement entropy data? So this is some typical features in the so following the Liu and Dakanaki formula, the entanglement entropy can be determined by this form. So here, so usually to determine the subsystem size and entanglement entropy in holographic setup, we need some information. So we first know that what is the background metric. Also, we need to know what is the some turning point. So turning point is related to the size of the subsystem. So this is some typical form. So if we know that the entanglement entropy, so we want to construct the same entanglement entropy by finding the some function f and u0. So if we determine this form as a function of u0 and the background metric, then we can determine if we find this unknown function f from this data, then the dual geometry is exactly determined. So to find this unknown function, we use some machine learning technique, because so here we consider some black hole geometry. So at horizon, the metric becomes 0. So usually when you're calculating this quantity, so inverse of the metric is appeared. So if there is a small error, numerical error, then at the horizon, that such kind of small numerical error gives rise some very large error. So to distinguish, to avoid such kind of problem, we use a machine learning technique. Okay, so this is some main formula. So applying some machine learning technique, we want to find the f. So changing the u0, if we all the value f as a function of u0, then we can reconstruct the dual geometry. Okay, so I skipped all detail. Then I will explain that some known result. Okay, so first we consider three-dimensional case. So this is simply BTG black hole. We know that already some metric form of the BTG black hole. So using that BTG black hole, we can also calculate the entanglement entropy. So that is the entanglement entropy. So the dual theory of the BTG black hole is a two-dimensional conformal field theory. So two-dimensional case, we know that we can calculate the entanglement entropy, because so two-dimensional theory, CFT is some very special, because it has infinitely many conformal symmetry. Also, it has some modular invariance. So using those large symmetry, we can exactly determine the entanglement entropy.
So you are questioning the non-logic.
Oh yeah. So yeah, so that is a two-dimensional conformal field theory result at finite temperature. So in this case, the dual geometry BTG black hole has this Blackening factor. Okay. So yeah, so we starting from this one. So this is some data, quantum field theory data. So we try to find this dual geometry. So here, using this machine learning, so yeah, we already know that this one, ln SE, and we've tried to find u0 and a known function f, which gives rise this known result. So this is some our result. So here, so this is a regular function. So there's a, yeah, so this is a numerical, so there is some numerical error, but so you can see that the machine learning result is almost same, the expected result, right? So here, so the orange curve is some original, so exact metric function, blackening factor, and the dashed black curve is some our machine learning result. Okay, so
Why there is oscillation near the orange?
oh yeah, so also when you're calculating this one here, so there's some UV divergence. UV divergences occur at U equals 0. So we need to appropriate regularization or denormalization of this one. So at initial point, so the such kind of the numerical error when you're applying some denormalization of that UV divergence, so that gives some correction.
So what happens if you use the other method?
So the other method, you mean?
I don't know, but anyway,
Oh yeah, so the other method.
there is no the other method to determine the.
Yeah, Oh yeah, so this is what? So the goal is starting with some quantum field theory result. We try to reconstruct the dual geometry. We usually so we assume there's some dual geometry, and then we calculate the quantum field theory. But in that case, we don't know what's the dual quantum field theory of the given dual geometry. So the goal is we want to reconstruct of the dual geometry of the some real physical system like condensed matter theory or QCD. Yeah. So for example,
No, he says you use the machine learning method to get the value function.
okay.
Do you have any other method like Taylor expansion or
Oh, so Taylor expansion, yeah. So you can use Taylor expansion. Yeah, still the oscillatory behavior in this initial position is
maybe the rotation is right? No.
no, still small, but it's not unavoidable. Yeah, so this is caused by some small data. So yeah, so this is related to the initial value. We should take some initial value. Usually there is some small error, but we integrating such kind of error, then that error is finally disappear. Yeah, so this one thing is this is a non-perturbative result. So if you're applying some perturbative expansion, then so I didn't draw here, but so similar. So in the some frontal region, so result is the same. But if you applying the perturbative result, then in this region, the perturbative result is a deviate from this real result, because so in this is horizon. So near this horizon, the perturbative calculation is invalid. Okay.
So you mean that 10036 determined by the machine learning method?
Yeah. So using this one. So this is a small error. So this is the expected one is 1 plus 1 U over UH. So that's the exact result. Yeah, so that is the known case. I consider some another case. So this is known as a string cloud geometry. If you consider some open string, uniformly distributed open string in ADS space, then the three-dimensional case, the blackening factor is appears this form. So this is also known. But in this case, we don't know what's the so we can calculate the entanglement entropy, but there is no analytic term. So however, if we're calculating the entanglement entropy, then here the blue curve is the entanglement entropy of the finite, the conformal field theory at the finite temperature. But if we consider string cloud, so this corresponds to, we consider some medium composed of some very massive particle. So in that case, the entanglement entropy shows follow this so orange dashed line. So that's a numerical result. So in this case, we don't have any analytic form, but still in this case, using this numerical data, we reconstruct the dual geometry. So this is the expected form. So here we want to determine this regular function. So in this case, so machine learning result gives rise to this result. So this is some numerical data that is almost same. It's almost constant near the 1. So the exact value should be 1. So this is well matched. And the final example is we consider some entanglement entropy. So we
Excuse me, we are behind the schedule. Please finish.
Oh yeah. So this is the last thing. So we consider some general things. So we don't know what is the dual geometry and what is the some dual quantum field theory. Anyway, so if this result is given, so we take some specific example. So in this case, we can so there is no any information about some horizon and some regular function, some Blackling factor. So compare to see this one, we can determine from the IR form the horizon appears at the A/2. So that is the position of the horizon. We can determine the horizon position from this entanglement entropy, and we but still we don't know what is the regular function. So okay, so applying this machine learning technique, then this is some result. So here, so original orange line is the original data. So derive this some result, and the dashed line is the result of the machine learning technique. If we applying some perturbative technique, then so perturbative technique in this small region, the perturbative result is also consistent, but in the large region, the perturbative result is different from the some real result, because so in this region perturbation is not valid. So from this known metric, we can also determine the entanglement, summer entropy and temperature, and so internal energy of this some system. We don't know what is that system, but which allows these types of entanglement entropy. Then we can see that the thermodynamic property of the system is given by this one. Yeah, so this is some simple approximation. So here, so the main goal is we want to know the dual geometry of some condensed matter or quantum condensed matter physics and QCD. So we try to reconstruct their dual geometry by using some machine learning technique. So this work can be also generalized to non-summer system. So in that case, we need more information about, so to describe some change of this theory along some algebra, we need some new parameter like a coupling depending on some energy scale. If we have some data of the coupling, then we can I think we can reconstruct the dual geometry of the system. So if that is possible, then so this gives rise some hint to reconstruct the dual geometry of the real condensed matter physics. So I will hope to report some interesting result in some future presentation. Okay. Thank you for your attention.
one brief question.
Okay, questions. So it is quite interesting work. So then, what kind of algorithm do you use in machine learning?
Oh yeah. So yeah, in this case, I use not I. So Dr. Sejin used some Adams technique. So that is the yeah. So we already know some exact result, and we can calculate this one by choosing some original any some function f, and then we compare the difference of this calculated one and original one. Adam's technique make this error is become smaller. So it's roughly reduce the error between the calculation and the original work. Yeah, so that is the some one of the technique in machine learning.
Okay, let's thank the speaker.